We finally got the IXL.
Can we go one more? IXL? Fruit bars?
IXL.
Isn't IXL like a fruit bar thing?
No, I just Excel bars.
Yeah, this one's a bit more complicated now because remember how I said that this only works for like linear functions, right? Yeah. You can't just apply it to this because I said if there's a coefficient you can just leave it there. I didn't give you one, I should have, but yeah. But if there's another function there, it doesn't quite work right. Yeah, because remember, anytime you're working with functions multiply and divide together, it's just not really pretty, right? So what we again have to think about is actually just go back to another example that might look like this, right? Because at the heart of it, what is this? This is a question where you have a nonlinear function inside the brackets there. So if I had, for example, y is equal to, what have we got? X cubed plus 1 cubed, right? And if I take that derivative, what ends up happening is that you take the derivative here, we drop the power down, and we drop this by 1. But what happens on the outside now, do you remember? Because we're not just taking the number in front, really. We're actually taking the derivative of the inside. So we get 3x squared, right? You put that all together, you get 9x squared outside. So, I guess we kind of want to think about what's going on here.
So you want to
Find the derivative of the
Yeah, that's right. When you're taking derivatives, right? So, if you have two things multiplied together and you want to take the derivative of this, you would have to use product rule, right? But that only works when you're finding derivatives. Here we're going backwards. And there's no actual like reverse product rule as far as I'm aware.
Can we just find the derivative of what's inside and then divide by...
Well, okay. So the thing is, right, if you have the derivative of the inside on the outside, it actually makes your life a lot easier. Yeah? But then you also have to kind of consider like what kind of power situation is going on here, right? Because over here, right, you'd have 3x squared, and you have this multiplied by 3 as well. So there's a few things at play here that we just have to kind of work out, right? It's kind of weird.
You divide that by, what would be beforehand? 6 times the derivative of the inside thing?
6 okay, so...
Like n plus 1
Yeah.
times the derivative of what's in the bracket.
Okay. Let's build it brick by brick, right? Or part by part. So you've got this thing here. We know this is going to stay the same. What's going to be the power now? 6. N plus 1 is 6. Yes, right. It's good. You're building the formulas, right? And this is only going to work now when you have... don't worry about coefficients. You can kind of do things with that, right? But as long as the power is 1 less than that, you know that you've got it in the right form. Yeah? So when I look at this now, I want to think, okay, how, when I take the derivative of this, do I end up with 8? That's what I'm thinking about. And I've already got this part here. If I took the derivative inside, I get 8x cubed. I'm also kind of I've got this 6 here that I want to think about. So what did you say we should do with this? You just put 1 on 6, which you normally do anyway when you think about powers, right? Because you put the new power as a denominator so that they kind of divide through. And again, checking this looks good to me, right? So again, formulaic way, like this is like an intuitive way, and the more of these you practice, that's why I'm giving you quite a few of these to practice, the more comfortable and confident you'll be with these forms, yeah? So I guess a formulaic way of doing it, if
Wait, it's gonna work every time though.
dy dx.
It's always the. But it's just that, but like that was a derivative.
It wasn't even, it was, right? But like this one here, we could go back, right?
Yeah.
As long as it's the power less. What you have to do is you have to be careful about these like coefficients here and how they kind of work, right? But as long as you're putting the new power underneath there, that's all you need to be thinking about generally, right? But here's like the formulaic version. Let me just write it for you. So if it's equal to f dash of x, like there's two ways of doing it, right? There's one way where you try and make sure you've got, how do I say this? Like, because you were saying, what if you don't have the exact derivative in this numbers here? Like, it relies on just like playing with the numbers a little bit. This one?
Inside there, right?
Yeah.
It was 7x instead of just 7.
Where? This is 7x?
Yeah.
Then outside you'd have to have the derivative of that in some form.
What if you did that?
Then you can't do it. That's why.
They're not gonna give you
Yeah, it's a very strict kind of expression. Like it needs to be in a particular form. So you basically need to have the derivative of this outside, of the inside on the outside part, otherwise this won't work. Yeah. Yeah. Huh? Yeah, right. And when I say derivative, I mean like some form of the derivative. It doesn't have to be exact. Like this one here, the derivative of the inside is actually 3x squared, right? So you can do this in two ways. You can say, all right, well, why don't I try and get the derivative of that? How do I get that? I want to introduce a 3, but by doing that, you're changing the expression. Yeah, so you don't really want to be doing that. So what they'll do is they'll say, okay, let's put the 3 here. But to address the fact that you've changed the expression, you have to do something that reverses that. Like what's the opposite of multiplying by 3? Dividing by 3 or multiplying by 1 on 3, right? Yeah. So when you write it in this form, what you can now do is you can just say, well, the primitive, if I took this guy here, that would be x cubed plus 7 all to the power 8, right? And then because of the fact that you have the derivative here of the inside here, you can just kind of use this expression now, keeping in mind you've got the extra 1 on 3 there, right? So we've got 1 over 3 here. And then remember, you have to put 1 over n plus, because we didn't actually have f dash of x on the outside, right? Can you see that? I don't know, is this a separate question? Yeah, it is. Sorry, that's kind of confusing. X. Yeah.
Can you just do x squared over
So you just put that in later. Well, like, then when you differentiate.
So I haven't finished yet, right? Then you need the new power, right? 1 over new power, yeah? So 1 over 8 here. And what's...
So we have to put the, so is it 1 over 24?
Yeah. So if you take the derivative of this guy, you'd get 3x squared times 8. So you get 24x squared, and that's how you get that.
Where did that 3 go now?
This 3. Yeah.
Next line.
Yeah. So how did I get to this next line?
8 times by 3, but it's divided by 3.
That's the primitive here. So as in like this thing relies on the fact that you have the derivative of the inside on the outside, right? And if it's not the exact same derivative, what they'll often do is like, can you manipulate it in a way so that you have it? So that's what I did here. So I said, okay, let's multiply this by 3, because the derivative of this is 3x squared. So you multiply this by 3, but you're changing the expression away. You're not actually allowed to do that. You're going to multiply by 1 on 3 outside here. That means that you haven't changed the expression, but that has to stay there throughout the whole thing. Yeah. Does that kind of make sense when you do? Yeah. So again, like this is not a foolproof way of doing it, but it's just one of the ways.